Okay, so the lens maker's equation was this: 1 over f is equal to n minus 1. What is n standing for? What is n for? What is n standing for? What is n? N is the refractive index. N is the refractive index of the material of the lens, whatever lens it is. So R1 and R2 are the radii of curvature. So if I'm going to have a lens like this, if I have a lens like this, the radius of curvature of this surface, R1, if it is 40 centimeters, and if the radius of curvature of this one is R2 is 30 centimeters, 30 centimeters. Okay, the radius. So radius of curvature is basically like what is the radius of the sphere that is formed from this surface, and what's the radius of the sphere that's formed from this surface? That is 30. Okay, so R1 is 40 and R2 is 30. Now, into this equation, you have to use the sign conventions. Now, you know sign conventions for so many things, but what is R1 sign convention? So the radius of curvature, radius is positive for convex surface, and radius is negative for concave surface. Okay, so you have to just look for whether it's a concave surface or convex surface, and then put the signs accordingly. So look at this one. This material is 1.5, refractive index is 1.5. Let's say it's glass. What kind of a shape is this? You're always looking from the outside, okay? What shape is this? Convex or concave? Concave. And therefore you have to take it as negative. What shape is this? Convex. You get it? Since this is convex in shape, you take it as positive. And this is concave in shape, take it as negative. So how do you find, how to use that equation? 1 over f is equal to 1.5 minus 1. That is the refractive index minus 1. And within brackets, 1 over R1. In this case, R1 is 40 centimeters, but it is concave. And so put minus 40. Plus 1 over R2, which is 30 centimeters and it's convex, and it's just positive. Positive. And then you work that out. So 1 over F is equal to 0.5 times 1 over 120. And F is equal to 240 centimeters. Focal length is 240 centimeters. So this, and is the answer coming out positive or negative? The answer is turning out what? You're wondering how this one comes out here?
Yeah.
Least common multiple.
Oh, we're adding fractions. That's not
Fractions. So if I have to do this one, 40 and 30, what is the least common multiple? It's 120. 40 goes how many times in 120? This is the method I have learned. And there are many methods, but this is very a safe method when you actually do this process. Even if there are variables, you proceed the exact same way, much easier. 40 goes how many times here? 3 times. 3 times negative 1, negative 3, plus 30 goes how many times here? 4 times 4 times 1 is 4. So 4 minus 3 is 1. So 1. Make sense? And it's kind of, this procedure is kind of useful and helpful even if there are variables involved. Like, suppose you have x over 3y plus 3x over phi y. So what you have to do is, what is the least common multiple of these two? 15y. 3y goes how many times here? 5 times. 5 times x is 5x plus 5y goes how many times here? 3. 3 times this is 9x, and it is 14x over 15y. Make sense? So I mean the procedure is exactly the same, and you can get to a final solution much faster by this approach. That's what I've learned. But of course you can do it any way you want. You can do it any way you want. Multiply the top and bottom with the same number to get the same denominator. Those kind of things. Well, once you have this wonderful tool, which is your calculator, you can always do it with a calculator directly, right? So what's the answer? Positive, negative? Implies what? That this lens behaves as what? Convex. The whole lens is behaving as a convex lens. Make sense? And there is another way of looking at it. Look, is it thicker in the center or thinner in the center? Thicker, so it's convex. A convex lens will always be thicker in the center. A concave lens will be thinner in the center. Make sense? So if someone needs to wear a contact lens which actually is convex, then that will be approximately the shape of the lens. Why? Because it has to fit onto your eye. So the side that hits your eye must be curved with the shape of the eye. You can't actually do it anywhere else, right? So this is the shape of the contact lens if it is supposed to be positive power. Now many of you are wearing contacts which are negative powers, right? Most of you. Negative power. Negative power means it's concave. That means it's supposed to be thinner in the center. So your lens, of course, since it is supposed to sit on your eyes, it's supposed to shape like that, but the outside is supposed to be shaped like that. So now it's thinner in the center and thicker at the edges. Of course, it won't be having sharp edges like that, kind of rounded off. So what happens, you can see, is thinner here and thicker here. So that acts as so your contacts are pretty much like this. Both are shaped the same way, but this is thinner in the center and this is thicker in the center. Make sense? So contact lenses are kind of made, that's why it's called lens maker's equation. They're made to proper shapes like that. So this one comes out a positive. Now, what is the power? Power of this lens is 1 over focal length expressed in meters. So it's like 1 over 2.4, and it's positive. And therefore you get 0.4 something.
0.417. Or it's 416 repeating.
Okay, 0.42 diopters. So this lens has a power of 0.42 diopters. Make sense? Okay. What's the focal length of this lens? That's 40 centimeters, and that's 40 centimeters. What's the focal length of this lens? Zero means what? You know what do you mean by zero? Zero focal length. Okay, so that means if you have a beam of light coming like this, and if you say, so focal length is the distance from the mirror, from the lens to the point where it touches, right? And when you say zero, it's going to be here. So what is it? Huh? Infinite. And you can see from that equation, 1 over f is equals to 1.5 minus 1, 1 over negative 40 plus 1 over 40. One is negative 40 and the other is positive 40. So therefore you get the answer 1 over f is equal to 0, and so f is equal to infinity. And what does that mean? That means this, after the rays pass through here, they will go straight and they will meet at infinity. That means they're not converging or diverging. Make sense? So basically what's happening is this lens is not a lens. When you call something a lens is when there is thickness difference. If there's no thickness difference, how can it be a lens? So a lens has to have thickness variations. Then you can call it a lens. Okay? If there's no thickness variations, then you can't call it a lens. That is a convex lens. Thicker in the center, thinner at the edges. This one is concave lens. It's thinner in the center and thicker at the edges. It's concave. Now, if the lens that I've shown you here is this, the thickness is the same everywhere, right? So if the thickness is the same everywhere, it is not a lens anymore. It's just a plain glass. Just a plain glass. What's the shape of your windshield? What's the shape of your windshield? Is it like flat glass? No? Is it curved? Is it a lens then? No. Why is that not a lens even though it's curved? Same thickness. Same thickness. Yeah. Imagine there's a big bottle and you're in the center of the bottle. And you're looking outside. You'll just see people just normal. Why? Because the thickness of what is around you is just uniform. So it is not a lens. So you'll see it just normal. So if you have a circular glass, like a bay window or something like that, it's kind of circular, you will see through normally, right? There's no bending at all. There's no converging or diverging. Make sense? So you can see f is infinity, which means these are not converging nor diverging, so it's just plain glass. Your sunglasses, are they flat? They're curved, right? But it's not a lens. The thickness is the same everywhere. So if you take a sheet and just bend it like that, it doesn't make it a lens. It'll still be a see-through thing. Okay? So yes, that equation kind of helps you to understand that. When you keep lenses together, like suppose you put two lenses together like that, what would be the lenses? If the focal length of the first one is f1 and this is f2, the focal length of the whole thing combined is going to be f, such that 1 over f is equal to 1 over f1 plus 1 over f2. So when you have two lenses side by side, then 1 over f is equal to 1 over f1 plus 1 over f2.
Thank you.
And if the answer for f comes out positive, the whole thing acts as a convex lens. If the whole thing comes out negative, then it's going to act as a concave lens. Okay. So understand that if two lenses are kept like that. Now, what is a reciprocal of focal length? What is it supposed to be? Power. Reciprocal of focal length is power, right? So what's the power of the entire thing? It is the power of the first one plus the power of the second one. Yes, Jay? Power of the entire thing is going to be power of the first one plus the power of the second one. Let's say this one has a power of positive 2.5. And this one has a power of negative 2.5. So we have two lenses. This has a positive power of plus 2.5. This is minus 2.5. So if I put them together like this, or like this, or whichever way, or like that, whichever way I put it, if I put both of them together, one is positive 2.5, the other is negative 2.5, so what should be the power of the entire thing? 0. That's exactly what's happening right here. Why is the entire thing having no effect at all? Because one is positive power and the other is negative power. Powers add up. So when you're wearing contacts, the contact has a certain power and your eye lens has a certain power. Get it? They add up. So what is the actual total power that is needed for your correction? So those things are calculated based on that. So contact lens is actually a lens sitting on your eye. So your eye lens and the contact, they're basically like this. They're put together. Not for him. For him it is away. And then we have to deal things differently. So the proximity of that makes a big difference. So when you're wearing glasses, there's a certain amount of distance which is normally the norm, right? But so therefore the calculations are actually done based on that distance. But if that same lens comes extremely close or goes far away, then you don't have the same kind of visual effect. It changes. So when you take the lens like further away or nearby, the effect is not the same as wearing it at that distance. Okay? Combination of lenses. So you saw the combination of lenses. When lenses are put together, what happens? And let's work through a problem right here for combination of lenses. When lenses are actually put together, how do you actually do the problem? Okay, that's an important thing. So, first of all, you should know what is a real object and what is a virtual object. You should know the difference between a real object and a virtual object. Yeah, remember when we did mirrors and stuff like that, I never mentioned to you about virtual object. I told you like it is not something that happens all the time. So we just skipped it and we went to all distances are real, real, real. But now it is time to learn what exactly is a virtual object. So what is a real object? A real object is something that is actually kept in front of you, just like that. This is a real object. How do rays come from this real object to your eyes? Right? From a real object, the rays diverge. From a real object, the rays diverge. And rays that are converging like this, if rays are converging like this, we say that it comes from a virtual object because it's not really there. You see it? We say that this one is coming from a virtual object.
Do they converge like through that cross?
Yeah, but we are drawing this. I'll explain to you. So what is exactly happening over here is, okay, those are the rays that are diverging. And then it comes and hits the lens, right? You're going to keep a lens or something, it comes and hits the lens. So when you're asked, what is the object distance? Then you say, this is your object distance, DO. And DO is positive. DO is positive, right? Now, if you keep a lens over here, these rays are converging rays coming from somewhere. Definitely not on this side. And these are rays that would have converged here if the lens was not there. Right? These would have converged here if the lens was not there. And so this is considered as a virtual object. That is considered as a virtual object. And what is a virtual object distance? DO. It's kind of weird because virtual object, rays are coming from somewhere not from a definite spot, but they appear to be meeting at a definite spot on the other side. And so this distance where it would have met, that is supposed to be called virtual. So what is DO here is negative because it is not really there. Okay? That distance is not really there. I mean, this virtual object is not something that is formed. So understand the difference between real object, which is basically from any real object kept in front of you. So if you keep a real object if you keep this marker in front of a lens, of course it is going to be a real object. But these are virtual object situations where these rays are coming from an angle and they are appearing to come and hit here. Now, since it is a virtual object, it is not going to be really there, right? So you won't have a problem saying, all right, rays are coming from a virtual object. No, that is not going to be a problem because from where is it coming? They must be coming from somewhere. And so this virtual object situation can only be part of a different problem. It can't be a problem by itself. Make sense? It only can happen. These rays cannot come from nowhere. So it is coming from somewhere. That means it is part of a previous problem. Make sense? That is possible. Now look at this one. If rays are actually, if I keep a real object here in front of a plane mirror, let's talk about plane mirror. What is exactly happening here? Rays, they diverge, hit. What happens?
They bounce.
They bounce which way? Yep, they bounce like this. As if they are coming from here. And this is our virtual image. You get it? That is our virtual image. Now let's see what happens on a plane mirror. Let's see what happens on a plane mirror or virtual objects. So suppose you have a plane mirror like that. And suppose you have rays coming like this. Obviously, rays cannot come from somewhere by itself. It definitely will have a previous situation that is not explained here, right? So these are the rays coming. Where is the object distance? So you extend it, this is the virtual object. And this is the virtual object distance. Make sense? What will happen to these rays after bouncing? Where will it go after bouncing? They'll come here, and hit here. What kind of image is this? Real or virtual? Real. And you learned in plane mirrors, a plane mirror will always form a virtual image. But now it can also form a real image if the object is virtual. Right? It just flips it from real to virtual, virtual to real. So I can actually get this image on a screen because it's really there. And this is the virtual object distance, that's a real image distance. Now let's see how these are applied in problems. Okay? Got it? And just as a plane mirror experiences, you can also have the same situation for a curved mirror, a convex or concave mirrors. It can be applied everywhere. So once you have the main idea, then you should be able to do it. All right, let's do a problem, combination of lenses. Now, you don't have to have just combination of lenses. You can actually have combination of lenses and mirrors, but I'll just do a combination of lens situation. Suppose you have a convex lens whose focal length is 60 centimeters. The focal length of this lens is 60 centimeters. And you keep an object and you keep an object. $100 centimeters away. If you keep an object 100 centimeters away, I'm not going to draw a ray diagram the way I showed you earlier. We did the ray diagram just to see where the image is exactly formed, how it is formed, is it inverted, upright. We did all that stuff. But now I'm not going to draw a ray diagram. Instead, we're doing the calculation straight away. So, if the focal length is 60 centimeters and the distance is 100, where is the image formed? So, we use the equation of 1 over f is equal to 1 over do plus 1 over di. Solve it up. 1 over 60 is equal to 1 over 100 plus 1 over di. Remember, I've taken 60 as positive because it's a convex lens. And I've taken 100 as positive because it is a real object distance, right? It's a real object distance. So what is di? Go ahead, do it. What is di? And tell me if it's positive or negative also.
Positive 150.
Positive 150. So image is formed positive 150. That means it's not a virtual image and all that, it's a real image. So this is what happens. The rays that go from here, see I'm drawing two rays, just symbolic representation. And where is it supposed to hit? 150 centimeters away, which should be somewhere here. 150 centimeters away, it's supposed to go and hit there. That distance is 150. Right? So that's what we understood. It is, the image is formed. So when the object is kept at 100 centimeters, the image is formed 150 centimeters from this. So that is a normal problem. Now I'm going to bring the next lens. So if I bring the next lens and put it at a distance of I'm going to bring a lens and put it at a distance of 110 centimeters from the convex lens. So I put that lens over there. And if, let's say, the focal length of this lens is 100 centimeters. Now, is it positive or negative?
Negative.
That's negative because it's concave lens. So remember that. Nobody's going to tell you it is negative and positive and all that. They'll tell you concave lens of this focal length, convex lens of this focal length. So that's a diverging lens, and this is the focal length of the diverging lens. And so, where is the image formed? So, to find where the image is formed, we are going to use the same equations again. To find the image formed, you need 1 over f is equals to 1 over f1, no, 1 over do plus 1 over di. So you can start substituting 1 over f, which is negative 100. No, negative 100. Focal length is negative. do. For this concave lens, where is the object? As you can see here, these rays are coming in from nowhere. You see it? So it is not coming from a real, see, this is a real object.
40 centimeters.
This is a real object. So rays were coming, diverging from here. But these are rays that are converging onto this concave lens. So what kind of object is that? It's a virtual object. So what is happening is, do these rays go like that and meet here? They won't go there. They're not going to go there. So the rays are not going to be going there. They appear to be going there. So this becomes the virtual object distance. How much? Negative 40. See, that's the virtual object distance, negative 40. So you can substitute that now. 1 over negative 40. One over negative 40. So understand why this is negative 40, because these rays are appearing to converge to a point 40 centimeters behind the lens, and that's why you consider that distance as the object distance, and it's a virtual object distance, so minus. So if you work this out, you should be able to get di. Tell me if it's positive and how much.
Positive 66.66.
That's right, 66.7.
Yeah.
So positive 66.7 centimeters implies that this is going to hit 66.7 centimeters from the lens. That is a real meeting point. So these are actually going to meet there. So this is your image distance. So it's really going to meet there. So you can see the action of this. See, what is the function of this lens to converge? So you can see it's converging. And what is the function of this lens? Diverge. So it is diverging the rays a bit, but not too much, right? So it's diverging a little bit, but still it is ending up meeting on the other side. So you got the answer. Now let's find out some more. What if I keep an object here of height 2 centimeters? If the size of the object is 2 centimeters here, what's the size of the image? Okay. So now what's happening is there are two lenses, and each one is doing a magnification. Each one is doing a magnification. And what's magnification? Like the change of size, right? The change of size, that's called magnification. Now when you have two magnifications and you want to consider what's the overall magnification, you can use this equation. The overall magnification is the magnification of the first one times the magnification of the second one. You can use that. The first magnification times the second magnification gives you the overall magnification. So let's find the first magnification, M1. What is the magnification produced by this lens? So formula for magnification is minus di over minus di. So minus 150 over do 100. So what do you get? Minus 1.5, right?
Yeah.
What does the minus sign tell you?
It's concave.
In the magnification, if there's a minus sign, what does it tell you? If the number is more than 1, it is magnification. If this number is less than 1, it is diminished image, right? What does a minus sign tell you? That the image is
Inverted.
inverted. The negative sign tells you that the image is inverted. If it's a positive sign, that means the image is upright, the same way as it is originally. That's what it is. So we got a magnification of 1.5. Find the magnification of this one. What is M2? Minus di over do. So minus, what is di? 66.7. What is do?
Negative 40.
Negative 40. And that gives you 1.67, positive, right?
Yes.
You got a positive answer here. That means this lens didn't do any inversion. It just produced a positive 1.67 magnification. So what's the overall magnification? What is the overall magnification produced by both the lenses together? So it's like minus 1.5 times 1.67, Answer is minus 2.5. Yeah, it should come 2.5 if you don't round this. So it will be 2.5. Minus 2.5. What does that mean? That the image is inverted. 2.5 implies it is 2.5 times bigger than this. So what's the size of the image? If this is 2 centimeter object size, like this. If the object size is 2 centimeters, what's the image size? Multiply by 2.5, so it'll be, this is going to be 5 centimeters. But upside down. If this is right side up, this is upside down. Why is it upside down? It's because minus sign is there. Right? So it is magnified. It is magnified 2.5 times, but it inverts it also. So the image, final image is there. Any questions on this? So we studied combination of lenses, how two lenses like kind of deal with this object and produce an overall image somewhere. This lens would have formed an image here, but this lens corrects it and puts it here. Make sense? So you can't do this with one equation. You have to do it individually, get the new object distance, and then go to the next one. Doesn't matter if this is a lens or a mirror, you're going to do exactly the same process. Okay? Now this distance is an important thing. If I put the lens here, image is totally different, magnification is totally different. It's all going to be different. So the position of this lens matters a lot. The position of this lens matters a lot. Now let me bring this lens and put it together with this lens. I'm just going to put it together. I'm just going to move that lens and put it right here. So that is f is equal to minus 100. So I have this lens and that lens, they're put together. What's going to be the overall focal length if they are really contacted, like making contact? So 1 over f is equals to 1 over f1 plus 1 over f2. So 1 over f, the combination of this together, because they are sitting together, you can treat them together with this formula. So 1 over f1, which is 1 over 60, plus 1 over negative 100. So this is 1 over 60 plus 1 over negative 100. So what is that? How much? One over 60, and this is negative because concave, so I'm using negative 1 over 100.
150.
Positive, negative. So you're getting a positive 150. Now the positive sign implies that this whole thing acts as a convex lens. The positive sign in the focal length that you got tells you that this entire thing behaves as a convex lens. That's all it tells you. Alright, so now you have the combined focal length. Can you find the image distance? Find the image distance. 1 over DO plus 1 over DI is equal to 1 over F. And in this case, you're going to use combined focal length. So 1 over DO is 100 plus 1 over DI is equal to 1 over 150. So what is DI? Negative 300. That obviously means it's a virtual image that is getting formed, right? It's a virtual image that is getting formed. Negative 300 implies that these are not going to meet anywhere here. It's somewhere else. So what is this lens trying to do? It's a convex lens because it's plus 150. It is definitely, this is a convex lens, so it is supposed to converge. But it's not converging too much. This is supposed to have gone straight, but instead it bends it a little bit. This is supposed to have gone straight, but it bends it a little bit. It is not bending all the way down here, because if it was doing that, then you would have got a positive answer, right? Since you're getting a negative answer, it means that they are diverging still. They are going in that manner. So if you're going to look at those two rays from here, if you're going to look at those two rays from there, these rays appear to come from where? If you trace it back. If you trace it back all the way, it will be here. 300 centimeters away. So that's 100, 200, 300 images like this. And what image is that? Real or virtual? Virtual. So those two rays, these two rays are diverging, and these appear to the eye that they are actually coming from 300 centimeters behind this lens. And that's what you end up with. What's the magnification now? What's the magnification of that? Magnification is minus di over do. Minus, this minus is part of the equation. Remember that, okay? And di is negative 300. And do. So what do you see? You see the whole magnification is plus 3. The entire magnification comes out plus 3, positive 3. Positive implies upright. 3 implies 3 times magnified. So if this is 2 centimeters in size, that image is supposed to be how much in size? 6, and it'll be upright. So it'll look exactly like this. So it just magnifies it the same way. Okay. So you can see how things work out. So if the lenses are touching each other, then it's much easier. All you do is find the overall focal length and then just do it as if it's a single lens. And you can see these kind of ray diagrams are kind of meaningful, at least to understand the situation. Okay? But these cannot actually pinpoint where the image is formed. And the other ray diagrams that you've drawn can actually figure out where exactly it is formed. But these are just symbolic representation of how things go. Any questions on that so far? So we have touched upon so many of these things right now. Combination of lenses, Lensmaker's equation.
What if the lens isn't in air? Like the Lensmaker's equation?
Air, then nothing.
No, if it's not in air, like if it's like in water.
Oh, if the whole thing is in water, then you have to use the relative refractive index. Good question. Like if this entire thing, if a lens is immersed in water, if you put the entire lens underwater, and now you keep an object underwater, and if you want to find out where the image is formed, now this is radius of curvature R1, and that's R2, and that's N of the, this is N of glass, and this is N of water. So now you want to find the refractive index of glass with respect to water. Make sense? You have to find the refractive index of glass with respect to water. Water's refractive index is 1.33, and glass is refractive index 1.5. So what is the refractive index of glass with respect? So what is the refractive index of glass with respect to water? It's going to be refractive index of glass over refractive index of water, which is 1.5 over 1.33, 1.12. So the refractive index is kind of weak. Can you see that? So a lens underwater is not going to behave as a proper lens. You can see that clearly. And this applies to our eyes as well. Our eye. The human eye. That's a retina. That's a screen where the image is supposed to be formed. And that's a lens. And that is not air. What's inside?
Jelly.
It's a fluid, yeah. Some name. So you got a fluid there, a transparent fluid, which is like filling up inside the eye. So if you're looking here normally, this is air, and then it goes into the lens of some refractive index, comes out into a different refractive index, which is the fluid's refractive index, and then it hits there. Now suppose you go underwater. Then everything is affected. Your focusing is all affected, different. Because if you go underwater, it's not air anymore, it is water on the outside. Water on the outside, a fluid on the inside. So your lens has to do a bigger job of focusing things. Like it has to really bend more to get something focused. So if you're underwater, you may have difficulties in vision because it is not the same outside. Yeah.
They make goggles to make it where and you can see just as well in the water.
Yeah, because the goggles are actually in the case of a goggle, you mean as a lens? Yeah, you can actually design something which is actually kind of cancels that effect. That's possible. But normally what a goggle is going to do is just separating it from the eye. So it still is air in front of your eye. So it's still air in front of your eye, but then the refraction from water to air before it comes into your eye, that is always there. So the real depth, apparent depth kind of concept will still apply. So even when you're underwater, that will apply. Now what I'm talking about is without the goggles, if you just go directly and water is touching your eye, then this is water, that is a fluid inside, and this is refractive index. So the relative refractive index becomes pretty small, so which means it won't refract the same way as it is doing now. So your vision can be affected. Sometimes you may see things more clearly underwater than outside without glasses. Suppose you don't use glasses. You should try it out. You should try it out and see. Both should try. I have got positive power. Mine is positive power, which means my lens is curved too much. I'm not able to stretch it that way. And yours is negative power. Yours is already stretched and you're not able to shrink it this way. That's the problem. So yours is not converging enough. Wait. No, yours is not diverging. I'll draw the whole thing. It's better to draw and explain. Yeah, so a good eye is something that has a good power of accommodation. And what is the so-called power of accommodation? Power of accommodation is the ability of your eye lens, because the screen is always placed here. The screen is fixed. The screen is fixed. Like over here, the projector, the screen is fixed, projector is fixed. So the distance is already decided. So it has to have a certain focal point, that's it, right? So you adjust the focus, you adjust the focus. So your adjusting focus basically is moving the lens backward and forward. So you adjust the focus and keep it in one way, one position, because your image distance is fixed. And the same way here, this is your screen, image distance is fixed. Which means your eye should be capable of accommodating to whatever you want. Like suppose there is a certain distance called the near point. Now near point approximately is 25 centimeters for a normal person. This is normal eye. A near point is supposed to be 25 centimeters for a normal eye. That means if you are normal, you keep an object 25 centimeters from your eye, 25 centimeters from your eye, you should be able to read it just the best. Really good. Oh, can you read it like that? Yeah, you can read it, of course, here. Can you read it here? Yes, you may be able to, but it won't be that clear as it is at 25. So 25 is called the distance of, the near point or distance of distinct vision. It's called the distance, minimum distance of distinct vision, clear vision. So for a person who is having perfect eyes, 25 centimeters, you keep, if you want to read something well, you keep it at 25 centimeters and you read it. Right? Now, at the same time, you look at something that's far away, your eye immediately changes its focal length. All right, so let's see how the rays go from here to the eye, like this, and like this. Perfect. Now, what happens if you want to see something like a star or the moon? If you want to suddenly look at it, so I'm looking at this marker now. All of a sudden, I want to see a distant car. So my eyes quickly go there, right? The ability of your eye to accommodate quickly between this and that. How is it doing it? How are you able to see this clearly and immediately that one clearly? What is your eye doing during this little time? There's a lot of work done by the eye, and it's a good exercise too. So what exactly happens here? If you try to focus on something far away, this becomes parallel, right? These are parallel rays. Now what will happen to those parallel rays? They will converge here. They will converge here. These will actually converge here if this eye does not take any more action. So what should the eye do in order to get the image back there? What should the eye do? Okay. If the eye does not make any changes, it will focus here, which means it's not going to be clear for you. So the eye lens must be less converging, right? Less converging means what? Is this less converging or is this less converging? That one? So what should the eye do as soon as you try to look at something far away? Stretch it. It's supposed to do that stretching, and there are muscles attached here. There are muscles, ciliary muscles, and those muscles are the ones which are supposed to quickly stretch it and make you observe. So if you are seeing something from here, the eye stretches out like that, and your focus is perfectly there. That is a normal eye. Now let's talk about a defective eye. So what is happening in the defective eye?
How's the defective eye, man?
All right. Now there are two main kinds of defects. There are two main kinds of defects. Now this is a defective eye. Let's talk about my defect, which is called hyperopia. Mine is hyperopia. So what exactly is that defect? My lens. So if I'm able, okay, my problem is this. I can see things far away beautifully. Look, if anything is far away, I have no issues because the lens is like this and it's able to fit it perfectly. My problem comes when I try to look at something nearby. When I try to look at something nearby, the rays are supposed to go from here like this, and all right. Now watch this. When I bring when I try to focus on something that is nearby, okay. If my lens does not do anything, where will the image be formed? As soon as the object comes closer, what happens to the image? Image starts going further away, right? A convex lens, image starts going further away. So the image will be formed here. So what should this eye lens do to get the image back on the retina? It has to converge it more, which means the lens has to do this. And my eye is not able to do it. It's not, yeah, it is trying to do this, but it's not fully done. It still stays like that. So I need the help of... Right, so Look at this. My lens is not able to do that, so I need an additional lens. This is not doing its function properly, so I need an additional lens to bring it together here. You understand that? So that's why I need a convex lens. So my reading glasses, they're convex lenses, right? You've seen my reading glasses.
Yes.
Yeah. So those are convex lenses. So with the help of them, I am able to focus on some very fine readings. This is my issue, and it's called hyperopia. Your issue, some of your issue is this. Your issue is this. If something is nearby, you can see very well. Doesn't matter how close. You are able to see everything so clearly if it is nearby, because your eye is really able to get it focused there. Now what happens for you is if the rays are coming from far away, if the rays are coming from far away like that, if the rays are coming from far away, what happens? Alright, don't look at this, some other image. If the rays are coming from far away, your your lens is not able to diverge enough. And so, since it's not able to diverge enough, these will get focused here earlier. So you lose focus. And so you need to diverge those a little more. And therefore you need a concave lens in front. So it will diverge. So this will diverge and that will diverge. And actually you can see this. This will diverge and make it exactly go in the same angle. And then you should be able to focus it perfectly. This is called hyperopia. No, myopia. Myopia, hyperopia. I remember these by the length of the word. This is myopia, which means short-sightedness, small. Hyperopia, long-sightedness, which means far-sightedness. I remember that. So hyperopia is you can see things far away, but I can't see close up. You can see things nearby, but cannot see things far away. Right? And you need the corrective lens. That's myopia. All right?